Hey there, math fans. This video is going to be a little different. I have a few ideas based off of a talk I heard a few weeks ago and observations I've made and things people have sent me over the years. And this is not going to be a rant or anything else. Just a conversation about how we think about math in a perception I think might be out there. And I'm curious what other people think. I think there's a segment of my students and the general population that want math to be wizardry. They want it to be mystical. And I'm thinking of this because I get sent these things like this, and I'll talk about some of these in a second. And I don't think these are inherently bad, but these things where someone says, here's a magic scenario, give me your shoe size, multiply it times 5, add 50, multiply by 85, add this, do a subtraction, and hey, look at the cool things about this. I just did a quick search, and because I've been making math videos, I have all these videos that pop up that say things like, look at this trick. If you're doing 120 divided by 5, you cancel the 0, and then you multiply this by 2, and it gives you the right answer. And the one I remember the most was one that was sent to me by a family member that said it was this, like, it wasn't exactly this, I can't find it, but the statement was like, something that's never happened, nobody can prove it, take the current year and subtract the year you were born and it's your age. And all these sorts of things like this. And I'm going to talk about some of those and how to think about them. But I think what surprises me is that I think people want them to be true. They want math to be this magical thing that only smart people can do. And I don't know if that's right, but I think there's a little bit to that. And then I went to this talk, and this gentleman was saying how he teaches mathematical proofs. This is like sophomores in college that are wanting to go into math. And he said there's this perception shift, he thinks, in the last 10 years of he will prove something mathematically. Like, say, here's the axioms, he'll prove it. And even after it's proven, the students don't think of it as a proof. They think of it as, well, there's probably some place where it's not true. So there's this idea of objective proof not actually being proof, like nothing's ever proven. So that's interesting that perception has changed. So I just wanted to say a few things here. And I do think there's this interest in wizardry. So let me just give a quick example. If I walked up to someone and said, okay, tell me what 10 squared is. It's 100. Okay? And then I would say, okay, I want you to go one number above and below 10. So I want you to take 9, and I want you to take 11. And that gives you 99. And then I want you to subtract and see that you get 1. Okay? And I would say, okay, let's pick a different number. How about 7? 7 squared is 49. I want you to go 1 above and below 7. You get 6 times 8. It's 48. And you subtract and get 1. Well, that's weird. I could keep doing this. The way I'm presenting it, not that it's bad, but it's presenting it as if it's wizardry. And then you keep trying numbers, and I'm guilty of this. Sometimes I present something this way to get people excited. But what I want students to do is to ask why, and not think that it's something because I'm smart, because I am not smart. I've proven it in many videos. But I am willing to ask why and to try to explain why. And that's more of what math is. Not to prove you're smarter than someone else. It's to analyze things and try to explain why they're true. And so I'm not against these math puzzles and goofy things people post, but I do think that there's maybe a piece of it that is trying to, it gives the wrong impression of what math is. And so I worry about it, because some of these are like the most popular posts on social media. Like I said, family sends me these things all the time and says, can you explain this? Can you tell me which person's right online? And It's great they have this great passion for math, but what I would like them to do is sort of to try to codify and ask why. So a little bit about how we actually think in math is we either try to prove something, and the idea goes back is we make a collection of assumptions or axioms. We debate about those. There's a whole segment of should we include this axiom or not. That's a different level of math. But once you assume some axioms, we prove everything from those using logic and other bits and pieces. So we don't, if whatever we get doesn't match the reality of whatever we're studying, then we need to change our axiom. So people think of math in this weird way, but we're trying to model things or study something and codify it, and we want to prove it rigorously from what we have. So we think in terms of proof and counterexamples. And I don't want to claim an expertise here. I have taught a course on proof, but this talk that I listened to was very informative because it brought up this idea that not very many people think this way. In terms of, so when someone gives you a statement, you can either try to prove it or you can try to come up with one counterexample. And if there is a counterexample, then the statement's not true. And so you have these basically two directions you're going to go. And this comes up all the time in arithmetic. And that's one thing I don't kind of, when I'll see my students do something like this. They'll have 2 times 3 times x. And the students can't remember if they're supposed to distribute or not. I have a separate video on that. They don't know if this is 6x or if it should be, what I sometimes see students do is they'll do 2 times 3 times 2. And this, like I said, this is not around. I think this is a discussion. I'm curious what other people think in the comments. And they won't know, so this would be 18x. 12x. See, I'm not smart. And they won't know, is it 6x or is it 12x? And that's the moment when we go, well, can we prove it? Or can we give a counterexample? The counterexample here is easy. Just plug in any number you want. An easy number to plug in would be 1. 0 is not a counterexample because that doesn't, so you need to maybe try a couple numbers, but when I plug in 1, are they the same? This is 6, that's 12. That can't be true. So you can see how I think is, so even in arithmetic, I think, do I know it's true? Well, I don't remember what the exact theorem was. Can I find a counterexample? Yes, right away. So that just gets rid of that. Most algebra mistakes we could quickly check by thinking this way. So I think there's some value here and why I decided I was going to do something else, which I still might do, which was kind of a gimmick, like against what I'm saying here. And so I'm trying as much as possible to avoid, to get back to this, which is I want people to ask why. And I want you to ask me why. You can even ask me. I saw this weird thing, but I'm not as into these little games here. And I want to encourage you to do the same. So if you're saying over here now, this example where I square a number and then I multiply the number above and below, and it always is 1 less. You could keep trying to find a counterexample, but after 2, and I always tell students to do 2 or 3 simple examples first. And if they can't find a counterexample, so you should always do like, I typically tell students to do the 3, this is my own belief. When you encounter something new, do the 3 simplest examples you can come up with, usually 1, 2, and 3. And if there are counterexamples, if they prove it's not true, then you're done. If it is true, they're going to give you some insight, initial insight. And then you start to think about why would it be true. And that's what we try to do in math. And it's not that bad. Typically the challenge is the labeling unknowns. And that's almost always the challenge in all these questions is this one solving method, which is to label unknowns. And it's amazing how often that is the stumbling block. If you are willing to label the thing you don't know and say, here's what I'm given, here's what I want, then you're probably going to get there. Okay, so in this case, The unknowns on the given problem, you might say, well, I know what they are, but the things I might want to label are these numbers. And you can't really over-label. You could label all of these, and including these and these and these. But the relationship is this is one less, this is one more. So what I would do, and there's little things people have to get used to. We like to, for whole numbers, we like to use n's in A's and B's. For numbers that could be decimals, we like to use x's and y's. There's no reason it has to be that way. It's just this kind of this routine. So let's have the starting number. Let's have n be the starting number. I don't know, what do we want to say? The number we will square. But I'll just say the starting number. And the point here is I don't need to, and this is just me. The moment I write that, I feel like I have a plan. And my plan is to label everything else. The 9 would be 1 less than the number, and the 11 would be 1 more. So what we're doing here, and this is where it's good I did some examples, is this is n squared. And I'm stealing this example from the talk I gave. I thought I have several other ideas, but it's a good little example. And then here we did 1 less. So how do we say 1 less than a number? We subtract 1. How do we say 1 more than a number? We add 1. And the moment you write that, if you know a little bit of algebra, then you have an opportunity to try to prove it. So I just am trying to illustrate this thought process of, in general, given a mathematical statement, we try to prove it, meaning we try to think of everything we know, but before we do that, we do 3 simple examples. Okay. So the statement here is that these two things are always within one of each other. And that's how I think. So when someone shows me something, I don't go, hey, that's wizardry. Somebody smart had to figure that out. I go, why is that true? And I would like my students to do the same. Why is that true? Can I codify it? Can I label? So in this case, we were comparing n squared to n minus 1 times n plus 1. And students probably know, I like to jokingly say this is a monkey face. Kind of looks like a monkey face. But this is n squared. And it's called a difference of squares because in the middle you get a minus n and a plus n. The nose is a minus n. The mouth is a plus n. So they cancel. And so then you just get minus 1. And then you compare these two things and you go, oh, I've proven it. N squared will be this, and this will be n squared minus 1. It removes the mystery. So I guess if you're someone that wants mystery, don't try to prove it. If you want to think of math that's mathematical, you can do whatever the heck you want. But I think this idea of that math itself is mysterious and you have to be a wizard, I want to dispel that. And I think sometimes in math, we do that. And I think everyone can do math. I think everyone can do well in math. I think most people like math in some way, even when they say they won't. There's a lot of room for things to be done in math. And so I'd like, if you see a post, don't get mad at the person posting and don't fight with the other people on there. It's great people are thinking about something mathematical. But let's talk about a couple of these things. So, when I saw this video, and it's not bad what the person's doing, but they're listing it as some miracle cure. That this is going to be, cancel this off. This is just one random video, so I apologize to whoever made it. I appreciate you trying to get math. And they say multiply times 2, and it's 24. Check it with a calculator, it's the same. And then they do 130 divided by 5. They cancel the 0, they multiply times 2. And at that point, I'm starting to go, okay, there's got to be a reason. I don't think it's a magic or mystery. I think, I just need to write down what's going on, and it will pop out what's happening. So let's see what's happening. So what's happening, and part of it is just how people write things sometimes. But if I was, how you go in math, you start to think of division as a fraction. And honestly, the moment I see the canceling, now this maybe comes from my experience, but this is a long time ago, someone showed me this canceling idea. But it's just if you divide by 10, it makes sense that it's going to be 12. You're not actually canceling the 0. It's just if you did the long division, we know it's going to be 12. So when I see that canceling, that's what it makes me think of. Now, it's not 10, though. It's 5. So what are they doing? They're multiplying by 2. They're multiplying top and bottom by 2. This removes the mystery and suddenly makes it not fun. So maybe that's bad. But they're just rearranging how they do this. They're doing 120 times 2, and then they're dividing by 10. But 120 divided by 10 is just 12. So that's that canceling that's happening. So when I see this, I don't think, this is wizardry. This is amazing. I just think, oh, there's a simple explanation for this. If we write down what's going on, we got it. So don't be sucked in by those. I keep having these math videos pop up because I've been posting them, and I would say the majority are like, look at this great trick, look at this magic. And it does bother me a little bit, but I also like that people are engaged, so I don't know how to feel about it. Okay, so let's grab some of the other ones. So this was on like the Today Show or something. I did a search. I was searching for weird math tricks, and they like had said this, and that really shocked me. So it says we have this mystery that when you plug this, take your shoe size, whatever it is, 7, and do all this stuff, you get your shoe size and your age. Whoa. This is an example of many things that are like this. So what I think when I look at this is, well, the thing that they're changing in the problem is the shoe size. So I would label that as something. X, Y, let's call it A. So they did an example for us, so I won't do an example. I'll just use an A. And I'm going to do all the arithmetic together. Typically in a thing like this, they're doing the arithmetic in pieces to disguise what's happening, which is perfectly fine. It's like any magician trying to do something, a sleight of hand. It says, I'm going to multiply this times 5, so A times 5. Now, if you know a little bit of algebra, you might write 5A. It's also fine to write A times 5, either way. And then what are we doing? Then we're adding 50. Okay. And then what are we doing? And I have this confidence that this is going to be easily explained. I didn't prepare it ahead of time. I just labeled the unknown, the beginning thing, and then I'm going to just do what we do. So it says multiply times 5, done. Add 50, done. Multiply times 20, so times 20, done. And whoever made this was trying to make it kind of look super mysterious. So they added this. Let's see what happens. I don't know what's going to happen. Let's see. They get this. And then take away your birth year. Whoa. So then we're going to subtract. For me, it's 1980. In fact, today is my birthday. That's what got me thinking about these ones. Okay, so let's do all this. And what happens? Well, you expand. Whoever made this expanded. They did this times this, and this times this. And that's like the whole trick. Why is that the whole trick? I'm going to show you. So 20 times 5 is 100. A plus 1,000. And I'm not seeing my way to the end. I just know. I have confidence in math. I like that it's reason. I don't think of math as wizardry. I think of it, I take comfort in the fact that it's not wizardry. And that it works out if you just write the things out. Okay, so you're going to get this 100 times A. If you know it, that immediately tells me why this digit is here. Because if I do 7 times A, I'm going to get 700. If my shoe size is 12, I'm going to get 1200. If my shoe size is 8, I'm going to get 800. That's why that digit is there. The shoe size thing was just an extra throw-in somebody thought would be funny. The other stuff is this. These two numbers add up to 2018. And this adds up to 1980. The funny thing about this is whoever made this in 2018. It's no longer valid. So this post was from 7 years ago. But for a year, people were amazed by this on Facebook or social media. This is not my age because it's not right. It's the age I was in 2018. So what was I in 2018? 2038. Oh, man, I'm old. So anyways, if you add that to this, you would get 738. My shoe size is actually 13, so if you add 13, it's going to be 1338. So I don't want math to be wizardry, and so I ask why. And I take a lot of satisfaction in why. There's other things I'd like to be magical, but not math. So it's a difference of opinion a little bit, and I feel like by thinking it's magical, you remove the fact that it can be done. This one bugged me. I had several people in my family send me something like this. The one I got sent said something like, it was like a couple years ago, and it said, take the current year, subtract the year you were born. No one in the world has ever figured out why this is true, but if you subtract, you get your age. That one really bugged me. That's basically the same thing that this is saying. Okay? So that bugged me on two levels. First is, that's how you figure out your age. So whoever wrote this thing no one solved is not exciting. But the other thing is there are counterexamples. Yesterday this wasn't true. Yesterday I was 44. Today I'm 45. So there's this simple counterexample. Depends on the part of the year. Okay, so anyways, another thing. This was on social media. I'm just finding things online. And people repost it. And that's perfectly fine, but I would like people, as they're reposting, to ask why. So it says, take your current age, 45, subtract your current age from 77. So it says, do 77 minus 45, and you get 32. And then add this to 1944. And you get 1976. And that's the year you were born, which is not true because I was born in 1980. Which tells me that this post on Facebook was 4 years ago. So this was just like a little bit of addition and subtraction. You could change your post now if you wanted it to be accurate to 1948. And then you could say, the year 1948 is the special year this year. And I'm not trying to be condescending or anything. I just want us to ask why, and I don't want us to think in terms of wizardry. Funny here because one of my friends sent me this when he saw I was making videos, and I'm not a political person in any way. I just thought it was funny. Square of the hypotenuse is equal to the sum of the square of the other two sides. It's all these people doubting him. So I want you to be a doubter. I don't want you to yell fake numbers in my class. But if you do doubt me, I would like you to give me a counterexample or explain a proof. Now, other things that pop up a lot are these little bits of arithmetic. I've gotten sent these things many times, these order of operation things. I think, there's various posts about these online of people trying to make it confusing. Now, in math, we do have an order of operations. They try to write it in a way that they force people to debate. People love to engage in these debates. A lot of it is convention. But typically the convention is we work from left to right and we do parentheses first. But this does highlight a different thing I brought up, which is if you do 6 divided by 3 times 2, and you do 6 divided by 3 divided by 2. I talked about this in another video. And you do 6 divided by 3 over 2. Those are some of those are different. 2 of those are the same. And this bothers students usually when they first see it. This is 1, because it's 2 divided by 2. And this is 6 divided by 1.5, which is 4. And this is 1. So these two things are the same. So the way in which you do your arithmetic matters here. I sort of don't even want to give an answer to this one, because I think people message me and they go, well, I did 3 times 3 and said it was 9. And I'm fighting with this person online who says that it should be something else, that it should be 6 divided by 6, which is 1. And we've been fighting online, and there's 5,000 comments, and everyone's yelling at each other. And I think it's this thing that, well, math is wizardry, or I'm going to prove I'm really smart. I can't imagine wanting to engage in a thing like that in the same way. This would depend. There was a time when the order of operations was different. It depends on your calculator, right? So, a basic calculator that doesn't do order of operations, if you type in 1 plus 2 and then multiply times 5, it does the 1 plus 2 first and gives 15. But if you're doing any sort of calculus or arithmetic or advanced math, we have to remove that confusion, and we have a set of rules that says parentheses first, then multiplication and division, and then addition and subtraction to help us settle these things. Because we really want this to be the same as some other thing, and there's reasons we want the arithmetic to be a certain way. So we do multiplication first. Is that how it should be? I don't know. That's the convention we use so that we don't have confusion when these things pop up. So typically the convention here would be is if this is multiplication, then you would do left to right. First you would compute this. You'd have 6 divided by 2. This is another reason we don't even use the divide symbol, and we like to use fractions instead. And we like to use these parentheses because it's kind of confusing. But we would do what's in the parentheses first. And I'm assuming they mean a multiplication here. And nothing else being given, then you would work left to right. And so it would be 3 times 3, which is 9. But, the fact that they wrote them next to each other, students do this all the time. An example would be the quadratic formula. I've seen this many times where the all over 2a causes them to get it wrong, surprisingly. So let me say what I mean by that. They'll be humming along. They'll calculate the top. They'll have something like -4 plus or minus 3 all over 2 times 5, let's say. And then they go to type this in their calculator, and they'll have -7 over 2 times 5, and they'll have -1 over 2 times 5. And then when they go to type in their calculator, they'll do -1 divided by 2 times 5 equals, and they'll say -2.5. And this is not -2.5, it's -0.1. Where did they go wrong? And it's because the calculator does order of operations. It does left to right. It doesn't understand that you meant all of this to be on the bottom. Because of that, I tell students they should always calculate this first, calculate the numerator, calculate the denominator, and do it in chunks. Okay, I feel like that's enough, but just something, I think the bigger thing is, don't think of math as wizardry. There's a logic in what we do, and there's a comfort in that. And when you're thinking about a statement, you're either going to try to prove it or come up with a counterexample. And that way of thinking is really helpful in many parts of life. All right, hope that's of interest.